I am Dr. L. Madhuchelvi, Associate Professor of Mathematics, in Sharada College for Women, Salem. In this session, we are going to discuss about extension fields. Let us see first the definition of a field. A field is a commutative ring with unique elements in which every non-zero element has a multiplicative inverse. Let us see the extension of a field. Let F be a field. A field K is said to be an extension of F if K contains F. Equivalently, K is an extension of F if F is a subfield of K. The degree of K over F is the dimension of K as a vector space over F and is denoted by degree of K over F. Let us see the theorem. If L is a finite extension of K and if K is a finite extension of F, then L is a finite extension of F. Moreover, degree of L over F equal to degree of L over K into degree of K over F. Let us see the proof. Let degree of L over K equal to M. That is, the dimension of L as a vector space over K is M. Degree of K over F equal to N. That is, the dimension of K as a vector space over F equal to F. Let V1, V2, etc. Vm be a basis of L over K. And let W1, W2, etc. Wn be a basis of K over F. Consider Vi, Wj, the set Vi, Wj, I equal to 1 to etc. M, j equal to 1 to etc. N. We have to prove this set is a basis for L over F. For that, let us take an arbitrary element V belongs to N. Since V1, V2, etc. Vm is a basis of L over K, V equal to K1 V1 plus K2 V2 plus an etc. plus Km Vm, where K1, K2, etc. Km belongs to K. Since K is a vector space over F, Ki equal to Fi1 W1 plus Fi2 W2 plus an etc. plus Fin Wn, where Fij belongs to F for every I and j. Therefore, we can write V as F11 W1 plus F12 W2 plus an etc. plus F1n Wn V1 plus F21 W1 plus F22 W2 plus an etc. plus F2n V2 plus an etc. Fm1 W1 plus Fm2 W2 plus an etc. plus Fmn Wn Vn. This is equal to, if you write, multiply and simplify that product, we get F11 W1 V1 plus F12 W2 V1 plus an etc. F1n Wn V1 plus an etc. plus Fm1 W1 Vm plus Fm2 W2 Vm plus an etc. plus Fmn Wn Vm. That is, V is a linear combination of the set Vi Wj, where I equal to 1 to etc. M, j equal to 1 to etc. M. This implies that the set Vi Wj spans L. To prove this set Vi Wj is linearly independent. For that, we can consider F11 V1 W1 plus F12 V1 W2 plus an etc. plus F1n V1 Wn plus an etc. plus Fm1 Vm W1 plus an etc. plus Fmn Vm Wn equal to 0. That is, F11 W1 plus F12 W2 plus an etc. plus F1n Wn V1 plus an etc. Fm1 W1 plus Fm2 W2 plus an etc. plus F, M, and W, N, V, M equal to 0 implies K1, V1 plus K2, V2 plus and etc. plus K, M, V, M equal to 0. We know that V1, V2, etc. Vm is a basis of L over K. So Ki equal to 0 for every I. That is K1 equal to 0, K2 equal to 0, etc. Km equal to 0. But what are K1, K2, etc. Km? K1 is the linear combination of W1, W2, etc. Wn. K2 is also like that and etc. Km. So we can write K1 equal to F11 W1 plus F12 W2 plus an etc. plus F1n Wn equal to 0. K2 equal to F21 W1 plus F22 W2 plus an etc. plus F2n Wn equal to 0 and so on. Km equal to Fm1 W1 plus Fm2 W2 plus an etc. plus Fmn Wn equal to 0. Since W1, W2, Wn are linearly independent over F, Fij equal to 0 for I equal to 1 to etc. M, j equal to 1 to etc. M. Therefore, Vij, the set Vij, I equal to 1 to etc. M, j equal to 1 to etc. N are linearly independent over F. Thus, the set Vij is a basis for L over F. Therefore, degree of L over F is the dimension of L as a vector space over F is Mn. So, what is M? Degree of L over K. What is N? Degree of K over F. Therefore, degree of L over F equal to degree of L over K into degree of K over F. Next, we are going to see the corollary. If L is a finite extension of F and K is a subfield of L which contains F, then degree of K over F divides degree of L over F. Proof. Suppose that L, K, F are three fields in the relation L contains K contains F. And suppose further that degree of L over F is finite. Clearly, any element in L is linearly independent over K or linearly independent over F. By our assumption, degree of L over F is finite. This forces that degree of L over K is also finite. Then also K is a subspace of F. Thus, degree of K over F is also finite. By the previous theorem, we know that degree of L over F equal to degree of L over K into degree of K over F. This implies that degree of K over F divides the degree of L over F. Next definition. An element A belongs to K is said to be algebraic over F if there exist elements alpha naught, alpha 1, alpha 2, etc. alpha n in F, not all 0, such that alpha naught a power n plus alpha 1 a power n minus 1 plus an etc. plus alpha n equal to 0. Equivalently, an element A belongs to K is algebraic over F if there exists a non-zero polynomial q of x equal to alpha naught x power n plus alpha 1 x power n minus 1 plus an etc. plus alpha n belongs to f of x such that q of A equal to 0. Next, we are going to see the adjoining field. That is, f of A is the subfield obtained by adjoining A to F. Let K be an extension of F. Let A belongs to K. Let that M be the collection of all subfields of K which contain both F and A. Since K belongs to M, M is non-empty. Since the intersection of any number of subfields of a field is again a subfield of it, intersection over M belongs to M, M equal to F of A. That is also a subfield of K. Since every member of M contains F and A, F of A also contains both F and A. Therefore, F of A belongs to M. Thus, F of A is the smallest subfield of K containing both F and A. So it is the subfield obtained by adjoining A to F. Next, let us see one theorem. The element A belongs to K is algebraic over F if and only if F of A is a finite extension of F. That is, the necessary and sufficient condition for an element is algebraic over F. Proof, let A belongs to K be algebraic over F. Since A belongs to K is algebraic means by the definition, A satisfies some non-zero polynomial in f of x. Let P of x be a polynomial of smallest positive degree in f of x such that P of A equal to 0. Our first claim is to prove P of x is irreducible over F. Contrarily, suppose P of x is reducible, that is, P of x equal to f of x into g of x, where f of x and g of x are in f of x. Since P of A equal to 0, f of A into g of A equal to 0 implies either f of A equal to 0 or g of A equal to 0. When f of A equal to 0, degree of f of x is greater than degree of p of x because p of x is of smallest positive degree satisfied by A. So, degree of f of x should be greater than degree of p of x. Similarly, when g of A equal to 0, degree of g of x is greater than degree of p of x, which is a contradiction because f of x into g of x equal to p of x, that implies degree of f of x should be less than or equal to degree of p of x and degree of g of x also should be less than or equal to degree of p of x. Therefore, a contradiction we get. Hence, P of x is irreducible over F. Next, we define a mapping psi from f of x to f of A by psi of h of x equal to h of A for every h of x belongs to f of x. To prove, psi is a ring homomorphism of f of x into the field f of A. Let g of x, h of x belongs to f of x. Then psi of g of x plus h of x equal to, you can write it as psi of g plus h of x, that is g plus h of A, that is g of A plus h of A, that is psi of g of x plus psi of h of x. Therefore, psi of g of x plus h of x equal to psi of g of x plus psi of h of x. But psi of g of x into h of x equal to psi of g h of x. That is g h of A. So g of A into h of A. So psi of g of x h of x equal to psi of g of x into psi of h of x. Therefore, psi is a ring homomorphism of f of x into f of A. Next, let us define V as a kernel of psi. What is the kernel of psi? That is equal to set of all h of x belongs to f of x such that h of A equal to 0. Since P of x belongs to f of x is of smallest positive degree such that P of A equal to 0, P of x is an element of lowest degree in the ideal. Let f of x belongs to B. That implies f of A equal to 0. If P of x does not divide f of x, then there exists A of x and B of x such that A of x into P of x plus B of x into f of x equal to 1, which implies A of A into P of A plus B of A into f of A also equal to 1. But we know that P of A equal to 0, f of A equal to 0. So the FHS completely becomes 0, but the RHS is 1, 0 equal to 1, which is absurd. Therefore, P of x divides f of x. That is, every f of x in V is a multiple of P of x, which implies V equal to the ideal generated by P of x. By the lemma, which states that the ideal A equal to the ideal generated by P of X of F of X is a maximal ideal if and only if P of X is irreducible over F. V is the, by using this lemma, we say that V is the maximal ideal of F of X. By the theorem, by applying the theorem, if R is a commutative ring with a unit element and M is an ideal of R, then M is a maximal ideal of R if and only if R by M is a field. Implies by applying this theorem, we get here f of x by v is a field. Since psi is a ring homomorphism of f of x into f of a with kernel v by the general homomorphism theorem of rings, which states that let R and R dash be rings and phi is a homomorphism of R onto R dash with kernel V, then R dash is isomorphic to R by V. So f of x by V is isomorphic to the image of f of x under psi. Therefore, the image of f of x under psi is a subfield of f of a. Also, psi of x equal to a and the psi tends alpha to alpha for every alpha belongs to f. Therefore, the image of f of x under psi contains both f and a. Thus, the image of f of x under psi is a subfield of f of a, which contains both f and a. But f of a is the smallest subfield of k containing f and a. Therefore, the image of f of x under psi equal to f of a. So, f of x by v is isomorphic to f of a. Now, we know that v is the ideal generated by p of x. So, since p of x is irreducible, the dimension of f of x by v as a vector space over f equal to degree of p of x. Since f of x by v is isomorphic to f of a, the dimension of f of a as a vector space over f equal to degree of p of x. That is, degree of f of a over f equal to degree of p of x, which implies degree of f of a over f is finite. Therefore, f of a is the finite extension of f. Now, let us prove the converse part. Conversely, assume f of a is the finite extension of f. To prove a belongs to k is algebraic over f. That is, it satisfies some polynomial over f. Let degree of f of a over f equal to m greater than 0. Then, any m plus 1 elements of f of a are linearly dependent over f because degree of f of a over f means the dimension of f of a as a vector space over f is m. That means the dimension is m means the basis of f of a contains m elements. Then any m plus 1 elements of f of a are linearly dependent over f of a. So let us consider the elements 1, a squared, etc. a power m belongs to f of a and they are m plus 1 in number. Therefore, there exists alpha naught, alpha 1, etc. alpha m belongs to f, not all 0, such that alpha naught plus alpha 1a plus alpha 2a square plus and etc. plus alpha m a power m equal to 0. That is, a satisfies a non-zero polynomial. P of x equal to alpha naught plus alpha 1x plus and etc. plus alpha m x power m belongs to f of x of degree at most m. Hence, a is algebraic over f. So, in this session, we saw the extension, the basic definitions of field and the extension fields. Some theorems and lemmas on that extension field. Thank you.